Welcome back, my statics friends. One of the most important concepts in all of beginner statics is the idea of forces and how I can add them together or break them down. The process of adding them together is known as finding the resultant, which we covered in the previous video, and the process of breaking them down into two or more subcomponents is called finding components, and that's what we're going to do today. So without further ado, let's get started. One of the easiest methods for finding components has to do with making assumptions about the coordinate system that we're using. And like most mathematics that we use in study of engineering, we're going to be dealing with the Cartesian coordinate system composed of an x and a y and a z-axis for 3 dimensions. Right? So that's kind of where we're going to kind of pick up. So if we look at rectangular components, what I have here is a diagram in which I have a force F, this guy here. And so whether I'm going to find this guy as a resultant of these two forces, Fx or Fy, or whether I'm taking him and breaking him back in to two pieces, I'm still bounded by some of those ideas that we talked about in the parallelogram law in the last video. Okay, that to fully define this vector, there is a, if we deal with a parallelogram, well, a special case of that parallelogram is a rectangle, and it's very convenient because that aligns up with our Cartesian coordinate systems of x to the right, y up, and then of course z would be out of the paper if you go with kind of a right-hand rule kind of thing. And so we'll talk more about some of these sign conventions here in a little bit. But what we can do is we can see that if I kind of work this thing backwards, let's suppose for now, let's ignore the f vector that's here and just look and say that I have two vectors, fx and fy. This could be my a, this could be my b, as we talked about last time. There is a parallelogram that can be constructed off of these, in which the resultant is the diagonal of that parallelogram. And so the parallelogram we're talking about is a rectangle. It's this dotted line. And so I can say that, oh, well, if that's the case, then if I were to draw this thing to scale, then I would know how long f had to be. That would be the magnitude. And so there should be probably a magnitude symbol on that guy. Okay, and that this vector with his magnitude is occurring at some angle that we'll call as theta, measured from the x-axis. Now there will be some other angles that we'll talk about as well that we can measure. I could measure him off of the y and tell the exact same story, and so those will be known as the direction cosines accordingly. But the idea is that we know that that we like to break things into orthogonal components. If I have my f and I want to break it into fx and fy, just because that aligns very conveniently with most coordinate systems that we're dealing with in engineering. Okay, now again, typically I set x as horizontal. That is not a requirement, but to be a Cartesian coordinate system, I do have to have x being 90 degrees to y. And there will be cases in some of the examples in future videos in which it will be more convenient to turn this or realign my coordinate system. It doesn't matter how we do it. As long as we're consistent, the math will take care of itself. All right, so the idea that we have here is that I have a vector, and if we go back to our vector addition idea, then what we have is we have fx plus fy is going to be equal to my f vector. That's the resultant. That's the vector addition of what's happening on these two guys. So all I have to do then in order to find the f vector is come up with a rule for fx and a rule for fy, and then do the algebraic sum of this. So all we need then is, typically I know the magnitudes. I just have to associate a direction with each of these magnitudes, and I have the vector piece that we want. Okay, now the basic relationship that we're going to take advantage of is probably one of the most important in all of vector mechanics, is this idea of, and I'll jump down a little bit, is that I can define an fx vector as being some magnitude times something that tells me the direction. Now, more generally speaking, what we're going to be looking at is saying that my f vector is going to be something about the magnitude, okay, multiplied by something that tells me its direction. Now, in the Beer and Johnson textbook, they like to write it as lambda. I prefer to write it as a use of f, meaning that it's a unit vector or something that tells me the direction that this guy is acting in. Okay, and so that's what we're going to kind of play with. So you'll see these two notations, but just be advised. I like to do it this way because this is a scalar quantity. I need a vector, and so I have to have a vector here that tells me the direction. Well, the Beer and Johnson book likes to write it as a lambda. In fact, it's an italicized lambda, which kind of breaks their sign convention. It's a vector, but it's not bold, and it's just kind of hard to see. So I'm going to write it as u sub f with a hat on it so that I know that the hat tells me that it's a vector. It's a little bit of kind of bookkeeping, if you will, to be consistent. It's one of the complaints I have about the Beer and Johnson text when they start talking about some of those. And that's not the only book that does it that way, but to me this makes more sense. And I call it UF for a reason, and I'll show you what that reason is here in a second. All right, so the U that we just saw in here, you know, this guy, okay, is what we call as a unit vector, okay? And unit vectors are very special vectors in which the vectors have a magnitude of 1 unit length, okay, meaning that the magnitude of U is equal to 1.0. Okay, it's basically just kind of, and what we can do then is that if I define the unit vector as a length of 1.0, and I can now multiply that by the magnitude of a force to actually get the full force vector out of it. So the way that we set this up, and there's some different forms of this, is that let's just imagine we're looking in the x direction. So here's my x direction, and let's start at 0.00, and let's move to 1.00. So my tail is at 0, my head is at 10. Okay, the length from here to here is now 1.0. Okay, well that would be a unit vector that tells me how to get from 0, all the way out to here. Okay, now if this is in my x direction, this gets a special label for our Cartesian vectors as a vector of I. Okay, it's just a very special nomenclature for this. Okay, and then likewise in the y direction, if I start at 0, and I go up to 1, no, now we're playing the same game again. That's 1.0, okay, and so this would be a positive vertical unit vector because my positive y direction is up. You know, before positive x was this way, so that would be my I. And so we're going to call that then as this, it's a bolded J. I prefer to write it as kind of a script thing with a hat, okay, so maybe you see it as, you know, something that looks like that in the book, or maybe it's bold. This is just kind of the way that I've always written it. Okay, doesn't matter as long as you know what it represents. Okay, and so here's my I, here's my J, and then of course in the third dimension in Z, you could go, you know, into from 0, out to 0, 1, and that would be a K vector. And if it points in the positive direction of the axis, which is what we saw up here, and this is positive version of the axis there, okay, well then this guy is clearly a positive I vector, and this guy is clearly a positive J vector, and so forth and so on. Okay, so if we play with that, those IJs and Ks are this UF vector. And so all I need then to create the vector that I'm looking at is the magnitude of that vector multiplied by something that tells me his direction. Okay, so if we jump down here, then what that means is that I can, a little bit of a focus problem here today. Maybe that's a little better. Okay, is that my fx vector then is the magnitude of the guy in the x direction multiplied by a unit vector I. Okay, in the y direction, it's the magnitude of the y component multiplied by unit vector j, and if the z direction vector is the magnitude of the z direction component multiplied by the unit vector k. And so those are the three methods that we have. Now what's cool about this is if I construct every one of these, I can now quickly turn it in and say, well, I can create my f vector then as simply being fx plus fy plus fz. Okay, and that's basically vector addition for three vectors. So before, when we were doing the parallelogram law, we had a condition that I can only do two vectors at a time. Well, now if I go to vector addition and do it with vectors instead of doing that graphical method, now I can handle three, or I can handle even more of these just by playing with the vector addition properties. Okay, and then we just kind of keep track of our IJs and Ks separately, and that will give us the resultant effect of what it is that we're trying to do. Now, down here at the bottom in the notes, you'll see this box. This is exactly that formula that I just wrote today. Vector A is the magnitude of vector A dotted into a unit vector in the direction of A. Okay, now, because this is a scalar quantity and that's a dot, okay, this is basically multiplying the scalar quantity into that. It's one of the dot product operators. Remember, to do dot products, you have to have two vectors. But again, we'll save that for a mathematics discussion, but for what we're doing, it's basically multiplication. All right, so that's what we're looking at. Okay, so if we take our formula then for my f vector, and we plug in, so here was my fx guy, plus here was my fy guy, plus here is my fz guy. Okay, that's the vector addition that we were just talking about that I wrote on the previous page. Well, let's do our substitutions in here. Well, here's my fx vector, which we just said was fx. Okay, now, again, what I've done is I've kind of cheated just because my camera's a little bit fuzzy today, and say that, that f of x magnitude is f of x. I mentioned in one of the earlier videos that eventually I would slip into this notation. This is getting into it a little bit earlier, but this is the same thing. Okay, I'm not worried about the bolds or the italicizer stuff, but if you see this, this is what I'm talking about. Okay, and so this is the magnitude of fx times I plus the magnitude of fy times j plus the magnitude of fz times k. It's just substituting in those three formulas that we had happening here. Okay, now, if we look at just the two-dimensional form of this guy, which means I drop off the z component, then we get a vector that looks like fxi plus fyj is equal to f vector. Okay, and so now with this, I can come in and I can find the magnitude of f as just simply being basically the Pythagorean theorem of all of this stuff, as we talked about. Remember, you've got kind of this triangle thing happening here, and I take x squared plus y squared gets me hypotenuse squared. All I'm doing is I'm playing with the scalar magnitudes of this. And with these two guys in rectangular coordinates, I can very easily come up with the magnitude of this. Now, if you're doing non-Cartesian components, we can always fall back on law of sines, law of cosines, but I have to know a little bit more angular data, because this one has the restriction that it has to be a right angle. Okay, so that's how you can get the magnitude of this particular vector. Okay, and that's all that we've done. It's the same formula as doing a squared plus b squared equals c squared. Okay, now, to find the angle theta that we saw in here, and again, angle theta is the angle that this vector makes with what would be my x-axis here, is that, well, okay, if we just play with the magnitudes here, that f times the cosine of theta gets me fx, and f times the sine of theta gets me fy, and that gets me these things. So if I take the bottom one and divide it by the top one, okay, well, sine of theta over cosine of theta gets me tangent of theta. Well, then the tangent of theta is equal to fy over fx. I now can back out what that direction is just by simply doing a little bit of trigonometry and so forth and so on. Okay, and so that's kind of the basics of where we're going with all of this. So let's give one a shot and kind of see what it is that we can do with finding components and finding resultants and so forth and so on. Give myself this way. Here we go. Get the right page here. Okay, so let's try one. Okay. Now, one of the things that we're going to look at then is that suppose that we have in space, and so here's my x and my y-axis, I have a vector magnitude f of 200 pounds, and it's acting at an angle of 40 degrees. So that's a 40 degree value here. What we want to find is we want to find the components of f that occur on the xy set of axes. So that's just our regular rectangular system. And then we're going to turn around and do it again and find the components of f that are acting on an x prime and y axes. Okay, so note the prime that's happening on there. All right, so let's do the first one first. Okay, so just like we talked about on this one, here's my f, 200. My fx then is going to be 200 times the cosine of 40 degrees, which is 153 pounds. And then fy is going to be 200 times the sine of 40 degrees. Now, don't fall into the trap of just assuming x is always cosine and y is always sine. It depends on where that angle is measured from, right? If I had called this as 50 degrees here, then fx would be the sine of 50. So this would be 200 times the sine of 50, and this is going to then be 200 times the cosine of 50 there. Okay, now again, the sine of 50 mathematically is equivalent to the cosine of 40, and so forth and so on. So don't get in the habit of saying, oh, well, x is always a cosine. It depends on where the angle is measured from. So because we had the 40 degree given to us, that's why we're using the cosine form. But you got to look at the picture. So that's kind of one of the pitfalls I see students make, is just watch that. And that's one of the little tricks that we'll do on a test or a quiz, is instead of giving you the angle from the x-axis, I'll give you the angle off of another axis, and then you have to know how to be able to find it. Okay, but it's still the same game. It's just, making that adjustment. So keep your eyes open for that. Okay, so those are my components on the XY plane. So 153 in the X direction and 129 in the Y direction of the numerical quantities associated with this XY plane set of components. Now, components, if you have a vector F, as we do here, to find components, they always come in pairs. Okay, so it just happens to be that this pair is a Cartesian pair that is 90 degrees to each other. Okay, they make a right angle. But let's go try another one in which that's not the case. All right, so the same vector, 200 pounds, measured at 40 degrees off the horizontal, and this time I'm going to set up an angle of 30 degrees below as being my X prime axis down there. Okay, so what we know is that if we go and play our parallelogram law, that there is a vector along the X prime axis, f of X prime, that goes down to some amount, and then there's an Fy vector along the y-axis, because y is still up this way, but these sets of vectors. So if I look at this, if I construct a parallelogram off of this, I can construct a parallel line across the top through the head of that resultant, okay, and then I can construct the vertical parallel to the y guy there. You've got your parallelogram, and this is the resultant that occurs across that parallelogram. Okay, now if I look at how far it is from here to here in what would be the x direction of this thing, you know, our vector we know is still f vector is f of x prime vector plus fy vector. Okay, and so what happens is we can kind of play around with our parallelogram and pull out one of those triangles. So the thing that we know, focus again. Okay, is that I know that 40 plus 30 is 70 degrees. This side is 20. Okay, I don't know this angle and I don't know that angle, although I can find this one. If I come back and I look at this triangle here and up, I know that if this is a horizontal line and that's a vertical line, that angle is 90 degrees. So if this is 40, then that has to be 50. Okay, and that's the math that I'm showing here. So this is 50 degrees. And so if this is 70 and this is 50, okay, then what would this one be? Well, I could do it by doing 180 on the whole triangle, or I can look at this little sub guy and say, well, that's 90 degrees. And so 90 minus 30 is 60. This angle would be 60 degrees. So when I pull that whole triangle out, it's the same game as what you played with the parallelogram law. We're just going to pull out the triangle parts. This is the triangle that you would get. I get a 200-pound side here, which is my resultant, 70 degrees, 50 degrees, and 60 degrees. This is my fx prime, and this is my fy side, because remember, parallelogram law says that this side has to be the same as this one, and the top side has to be the same as the bottom side of this. Okay, and now with this information, I can now go do law of cosines and law of sines, or in this case, just law of sines on this, and set up my ratios that I'm going to take my fx prime to the sine of 50 ratio, that's the side, is going to be equal to 200 times the sine of 60. Okay, and so I've got everything I need. I can compute that quantity, and I can do sine of 50 degrees, and I can solve for fx prime as being 200 times the ratio of sine of 50 to the sine of 60. And if I do that, this fx prime is now 177 pounds. Okay, and that would be the value of this force acting along that line x prime that makes up the component of this guy. Okay, and then do the same thing to get fy. So here's my fy side. Okay, and its opposite angle is 70, so fy to the sine of 70 is going to be equal to 200 times the sine of 60, and you do the math, you can find out that that y component is 217. Okay, now, what do you notice on this is that they come in pairs that, you know, even though fy was the same, you know, in the same direction along the same line, to make this up, the component of this is based on the value of the component of the other one. These two come in pairs. So here fy was 129, but now down here it's 217. Okay, and if you kind of think about it, that should make sense, right? That this guy has a piece of him that's also acting downward, that's fighting what's trying to pull him up, but the net effect still has to be constant. Okay, and then the x component of this guy, you know, obviously is in a different direction than the x prime, because my x prime directional is happening down there. Okay, so it's kind of an interesting way to do it, but remember that if you're asked to find components, you know, that you've got to provide, you know, that if you break a vector into components, you have to provide two of them. Okay, now they don't have to be Cartesian, they don't have to be right angles, typically they are, but they do come in pairs, and as long as you get both pairs correct, both vectors of the pair correct, your mathematics will work out exactly the same. Okay, so that's kind of what we're looking at, kind of what we're playing with there. All right? Okay, let's see. Okay. Now, using this idea, we can kind of get into a special type of vector, okay, which we'll look at here, okay, and this is what we call as a position vector. And what a position vector does is it basically used to locate 2 points. Now, when you get into your calculus classes and start dealing with vectors, they do position vectors all the time. And they write them a little bit differently in here, that this guy might get written as, some sort of bracketed, and that's, my x, my y, and my z might be the notation that they use. It's the same thing, right? That we're going to define a position vector, and I use r, because that's historically what's done in physics and in most calculus classes. Okay, that this r vector, if we look, is a vector that starts off at the origin 0, 0, 0 and goes out to some point p. So this is the trick that they do in calculus, and it wasn't until later that I realized that's what they were doing, that all of a sudden all of that stuff in my calculus class started to make a little bit more sense, that they're defining a point's coordinate, the coordinate of a point p in space as being the position vector from the origin out to that point. Okay, so if I say that my point P is at x, y, z, and my origin is at 0, 0, then the position vector to get from 0 to P is this guy. Okay, so R is xi plus yj plus zk, and so, or this bracketed xyz kind of thing. Okay, now if we look at this, now we're going to change our notation up just a little bit, because not always is the start point at 0, 0. Okay, so what I'm going to do is I'm going to define for a vector, let's just call the head at being at point B, which would be here, and my tail being at point A. This guy has coordinates of xb, yb, zb, and then A has coordinates of xa, ya, and za. All right, so the position vector that gets me from here to here is simply going to be the head coordinate minus the tail coordinate for each of the x, y, and z values. Okay, now if I break this into components, the distance that you're going in the x direction, which in this case my x-axis is coming out, and it's still a right-hand rule kind of thing, right? If I can kind of get my hand up here, thumb is, well, sorry, my thumb would be, it's hard to show. These are right-handed to each other, if you will. Okay, put your thumb on the X, your first finger on Y, and then the middle finger would be Z, would be pointing upward. That's a right-hand rule set. And so the right-hand rule set is very important when we get into some other vector operations such as the cross product, but for now we just use it to set up our Cartesian axis. So in this class what I do is I tend to bounce around between Cartesian directions. Sometimes X will be to the right, sometimes X will be out, sometimes X will be up, just to make sure that we're paying attention and watching that orientation. Okay, because at the end of the day, the mathematics will all take care of itself as long as I maintain that orthogonality and that right-handedness to this. All right, so what we're going to do then is to define this. All we're doing is we're doing this endpoint B minus the start point A for all of the I, J, and K unit vector directions. So here's my delta X, XB minus XA. Here's my delta Y, YB minus YA. And here's my ZB minus ZA, or delta K, or delta Z, I guess. Okay, and that would be the position vector to get from A to B. Okay, and that's all we've done on this. Okay, so if we take a look, we can use this now to start finding dimensional information, like, well, what's the distance in space between A and B? Okay, and it could be any 2 points in space. And so if my coordinates are, say, A is 1, 0, and minus 3, and B is minus 2, 2, and 3, okay, let's find the position vector magnitude and direction that gets me from A to B. Okay, so again, we're going to do our head of the vector B minus the tail of the vector A. Okay, and so my position vector to get from A to B is going to be minus 2 from the B, minus 1 from the X, times I, plus 2 minus 0, so here's the 2 and here's the 0 for the J, and then 3 minus a minus 3 from the K. All right, and so this vector, if you do the math, then is minus 3i plus 2j plus 6k. That's the position vector that gets me from A to B. Now the thing that's cool about this is now I can do a three-dimensional Pythagorean theorem on this guy, which is basically taking each of the components in the x, y, and z directions, squaring them, adding them together, and taking the square root will get me the magnitude, in this case, of my r, or in this case, my r from A to B. Okay, and if I do that, so I'm going to take my minus 3 squared plus 2 squared plus 6 squared, add all that up, take the square root, and you'll find out that the distance from A to B in this is 7 meters. And that's the distance in space between A and B. It's a straight line distance on this. So that would be my magnitude. Now my position vector, RAB, we know is minus 3i plus 2j plus 6k. Well, what we can do is we can come in and we can rearrange this a little bit. That if we remember the formula that I just showed you, where f was magnitude of f dotted into unit vector in f on this, well, I can change that and make that r is magnitude of r dotted into unit vector in r's direction. I can create a unit vector between any 2 points, okay, based off of the positional data. And what's cool is that this is going to give me the ability then to be able to direct forces along lines between known points in space. This works really well for, things like rope systems, or where I have a force in a rope. If I tie a rope to a wall and I pull on it with a force F, the force is directed along the rope. Well, if I know where the 2 points at the ends of the rope are in space, and I know my force is along that line between those 2 points, I can now start to play a game where unit vector of f has to be equal to unit vector of r, okay, because their magnitudes are the same and their directions are the same, and that allows me to now jump from positional data to force data and back and forth as I want, as long as I take advantage of these unit vectors. Unit vectors are very, very, very powerful. Okay, so I can compute the unit vector for r. I've got the position vector and I have his magnitude. Well, the unit vector for r here is just simply the r vector over the r magnitude. So it's minus 3/7 of I plus 2/7 of j plus 6/7 of k. All right, and what happens as I start to look at this is that we can now go in, and I can also go one step further and do something known as the direction cosines. That for any vector, u vector, that we can say that the cosine of some angle alpha multiplied by I plus the cosine of some angle beta multiplied by j plus the cosine of some angle gamma multiplied by k can be written as a unit vector. And if we look at that picture that I just showed you up here, you can kind of see some of these angles. Now this graphic is in your book, but I can kind of point out that all that it's saying is that the angle that the x-axis makes with the vector is what we call as alpha. The angle that we make with the y-axis is beta, and then the angle that it makes with z-axis is gamma. Okay, and now I've got basically the direction cosines, or the angles that are associated with that. Okay, and so if I'm willing to accept that, then I can come in and say, well, I've got my unit vector. Well, then this quantity minus 3/7 is the same as the cosine of the angle that the vector makes with the x-axis. So the cosine, if I take the cosine inverse, I'm just looking at the first term and comparing these two pieces here, that the cosine inverse of minus 3/7 is 115 degrees. That from the positive x-axis to the head of the vector along the x-axis is 115 degrees. Okay, it's kind of like a bearing, if you will. Okay, and then a beta on this then would be 2/7 is cosine of beta. That's the j terms, comparing them. So the cosine inverse of 2/7 is 73.4. Okay, and then the cosine inverse of 6/7 is 31.0. And now I have the angles that this vector makes with the Cartesian axis, just as simple as that. Okay, and so that's what we can kind of do with a lot of these. All of this coming out of just simple, basic vector components and this idea of unit vectors, which are just amazingly powerful in things that we do. Okay, and so unit vectors are used all over the place. You know, even for things like velocities and accelerations. If I know the direction of the effect, I can create a unit vector to define that direction, and then all I do is take the magnitude of whatever it is, the magnitude of the velocity or the magnitude of the force or whatever, and I can really easily construct the full form vector of this. I can basically construct this guy, okay? And then if I have him, and then I have multiples of these vectors, you know, I have 3 or 4 different effects happening at the same time, I can find the resultant of those by going back and saying, well, we know that the resultant vector we defined as being A plus B plus however many of them, and I can get the resultant of that system, and then from that I can go then and say, well, what's the magnitude of that guy? Well, when I add up all the I, J, K stuff, well, now I've got the ability to get the magnitude, and you can very quickly and easily move between these different vector pieces, and it's really, really handy, and it'll be a trick that we will do over and over and over again as we start to do forces in space. So I hope that's made some sense to you. This video is a little longer than I would have liked it to have been, but it's a very, very powerful concept. If you need to rewatch this, please, by all means, do so. For my students, if the video quality wasn't working really well, make sure that you're pulling up the lesson note packet so that you can kind of follow along with what's going on. I'll provide these notes to you guys as part of the class. So just make sure that that it's making sense to you. If you got any questions, as always, get with me. Leave me some feedback down below in the comments section. As always, if you found the video useful, please be sure to like and subscribe, and we will see you guys in the next video. Welcome to the world of vectors. Happy engineering.